Thank you, James. Thank you, everyone, for this opportunity, the organizers in particular, and everyone attending. I've been asked and tasked to present BHTOM, and my title was Why and How, and I'll split it into two parts. So I'll start with what and why, section first. So this will be more like first like a presentation, and then we'll move on to hopefully some hands-on session, quasi demonstration and quasi workshop like part of my presentation. So BHTOM was mentioned a couple of times, and I'm grateful. So this is the initiative we started some time ago, and I personally am a professor of astronomy at the University of Warsaw, as well as the National Center for Nuclear Research, both in Warsaw in Poland. And I've been doing this for something like 12 years now. Okay. And of course, there's many people involved in this. So there's a couple of faces of people most closely involved. People come and go, but this is Poland-based effort, but it also spreads to other institutions. So there's many people from other places as well, and we collaborate with many groups in terms of time domain and transient in particular. Okay, so I'll start with a definition of a small telescope because some we might have different depending who you ask actually. So for example, for radio astronomers, small telescopes are they're like 15 meters, right, in diameter. So in our case, we're talking about centimeters. And of course, we can think of classical professional small telescopes. So very often they are old. Some of them are very old. We work with, but there are also new telescopes being built by multiple institutions, research institutions with targets, with particular science in mind. They're dedicated telescopes, or they're meant to be training facilities. So very often they're located in the best places, astronomical sites in the world, but not necessarily the professional ones, especially the old ones. But there is also a growing community of amateur astronomers. There always been amateur community of astronomers, but these days I think this is the time when astronomers, the amateur astronomers, we shouldn't stop calling them amateur actually, because the equipment they have very often supersedes the equipment typically used by the professionals. I very often, when I look at some of the equipment amateurs have, I'm actually getting very jealous about that. And some of these telescopes are located in backyards of people's houses, but also they're located in nice sites like Chile or Spain. But there is another group of telescopes which are also growing in numbers and also in quality, which are operated by schools. Very often these are modern observatories, very often equipped with good telescopes, good cameras. Very often they're located in big cities or within the cities, so they suffer from light pollution most significantly, I guess. But still, they have a huge potential for science as well as outreach. And another part of the community is the outreach facilities themselves, like planetaria, or where the telescopes are being built with the outreach in mind. And again, they're often modern, but also located in big cities. So you see, this is a gallery of some of our partners we partner with. I deliberately, span the whole diameter range from 5 centimeters to 260 centimeters, because this is the range we work with. As you can recognize, the smallest one with 5 centimeter is the C-Star telescope S50, which actually currently we're very extensively testing whether this little toy in apostrophes, that if this toy is capable of delivering science. And well, I'll keep you updated, but we have some first promising results on that. Okay, and I'll show you a movie made by one of our partners. This is actually a school observatory. You'd be surprised, in southern of Poland, in the mountains, there's the good quality of air. So this is a robotized, remotely controlled telescope, 40 centimeter telescope, on the roof of the school. You actually see the church in the background, which is lit normally, but there is a remote the observers have, and you can switch off the lightning, the illumination of the church when you are observing. So there's good. So there's some community response as well. And this telescope, this very telescope, is delivering beautiful, scientifically valid data. I just showed this as an example. Okay, so the small telescopes, they can take part they have a lot of roles to play. So I come from transient community, so that's why I start with that. So they can participate in transient classification, spectroscopic and primarily photometric. Then the transient follow-up, observations of things which went bunk. So both spectroscopy, photometry, but also astrometrically. And in general, time domain targets, that's the term here, but this is what small telescopes can do for a long time. They can monitor targets which require time domain data. And it could be time domain photometry, time domain color, time domain astrometry, whatever you can think of. Then expanding, going a little bit away from my own expertise, but this is what small telescopes are often doing as well, small solar system objects and science behind asteroids, comets, and occultations, mentioned a couple of times. What is also growing, which is the involvement of small telescopes, is appearing in space situation awareness. So this is the tracking of near-Earth asteroids, objects, or potentially hazardous objects, but also space debris, tracking satellites. This is another avenue small telescopes are now playing part in. So the advantages of small telescopes are that they're flexible, they can respond rapidly, which is quite often very difficult with the professional telescopes and larger ones. And also the small ones, they can cover the bright targets, which are missed by large surveys. They build larger and larger aperture telescopes. They go fainter, of course, which is very interesting scientifically, but then they lose the bright end. And this is where small telescopes can contribute significantly. And of course, the outreach in science, this is what can be done with small telescopes, and that's why we are here, I think. Okay, so I'll describe the background of BHTOM, starting with the Gaia space mission. I hope everyone heard about Gaia space mission already. This has been a very successful ESA space mission, which has been tasked to observe the whole sky continuously. That was probably the only task, but with quite good accuracy, both in astrometry, and that was the main purpose of the mission, but also in photometry. So the whole sky was scanned for 11 years. And while it's been scanned, Gaia was delivering objects which changed. And here I have an animation showing some alerts reported by Gaia. This is what I've been involved from the very beginning. So we designed a system which was looking through the Gaia data and looking for things which changed, right? So there could have been a new object appearing, like a supernova, or star getting brighter, or a star disappearing. Essentially, any significant changes on the sky, astrophysically important, so that it's worth alerting. So that's the general purpose of all the alerting surveys. These days we have ZTF, we have Assassin, Atlas, LSST is coming online fairly soon, but Gaia is a good example of this because Gaia was in space. It was it was unbiased. It was observing the whole sky, both hemispheres. So hence, it was required to do something with these alerts, and that's why we established the alerting system in Gaia. And this is an example of an alert coming from Gaia. It's called Gaia 23 BAY. And you see the brightness of the star not changing for many, many months. And then suddenly the star gets brighter and significantly brighter, and not only once, but also twice. And if it wasn't the reaction of small telescopes, we would essentially missed the science case here. And this is the data collected by a network of small telescopes where, Gaia would essentially go further, observe further parts of the sky, and we would have missed this one-off opportunity to study this object, why the star got brighter. And in this particular case, this is also my favorite topic scientifically. This turned out to be a potential microlensing black hole, right? So we would have missed this scientific opportunity if it wasn't the response of the small telescopes network. And you see the brightness, the magnitude of this object is 1312. So this is very easily reachable by small telescopes. So we've gathered this network of telescopes. We started building this network from 2013 already with Gaia alerts in mind, but now with Gaia being over, actually January this year, this network is still there, and it's ready to react to any type of alerts, but also any type of time domain targets. So at the moment, the network consists of 130 telescopes with different sizes, different locations, as you can see here. Many of them are manual, some of them are robotic. Many of them are in good weather sites, but also there's telescopes in poor weather sites. Here is the weather map of the average cloud coverage in Europe. You see there's many telescopes involved, but many of them are located in poor weather. But because we need a lot of them, to guarantee the coverage both in time and sky. And that's why we need more, and the more the better response is, and also the more telescopes we have, the more targets we can actually observe. And many of these telescopes were just volunteering with their observing time. Whenever, if they have their own dedicated program, they could observe a couple of targets from our program in the gaps between their programs, or they donated a couple of nights of their time. And for some of them, we wrote the proposals. So it depends on the way the telescope operates. So now the question is your telescope there? And we would like to have your telescope in this network as well. We'll get there, I hope. This is an example of the data we've collected. This is a crazy microlensing event, but it doesn't look at all like classical microlensing because it's been going up and down. And it's Gaia 16 AYE, the event we discovered in 2016 and then observed for almost 2 years. You would never be able to collect such data. With Gaia alone, you would simply miss it. You see the black points. But with the coverage with small telescopes, we covered in multiple filters. You see different passes of the light curve. There are different filters. And we have covered all the features of this crazy light curve over a period of 2 years. You would never be able to do that with one telescope, with one proposal. So only a network can do that. So that's the power of network of small telescopes. And of course, we published this one, and we published many other papers. So since 2020, when we started fully operating, we've published something like 20, or it's a growing number actually, of papers, including the data collected by the network. And actually, we include all the observers. So if you contributed to that light curve, and your data was used in the analysis, then you're invited to become a co-author of a refereed journal. So here are some examples of these journals and front pages of the papers we published. Very recently, we published a paper on Corona borealis, which we have observed intensively. I'm sure everyone of you knows that one. And actually, we published not a very popular result because we actually showed that this one is not going to explode anytime soon. It will explode someday, but not tomorrow, right? And not tonight. But it was actually the data we've collected in combination with AVSO as well, but also some archival data. And we've gathered all the observers as co-authors on this paper. Okay, so what is BHTOM? BHTOM is this one of these toms designed by Las Cumbres Observatory. I'm sure everyone knows what Las Cumbres Observatory. They were pioneers in the networking of time domain observations. So they provided open source code for TOMs, for essentially target and observation manager. So we took it from there. It was an open source code, and we developed together with them to fit our needs, because our network is very heterogeneous in contrast to LCO network, which is very homogeneous. So we made this, we call it black hole TOM because it's a nice name. We observe black hole, but not only, of course, but we can have this nice logo. bhtom.space is an easy address to remember. So essentially, this is the central place. This is the web tool where we coordinate automated. We process the images from all these telescopes. And I'll spend some time on this because that's the main advantage of our system. And then we standardize. Everything is done automatically. We standardize the data so that this is essentially science-ready data. On top of that, we include all the archival multi-wavelength time domain photometry. So whatever is there on that target, we also grab it and present. So we're open to new users. It's free to use, easy to register. Just has to be, we have to be approved by an admin, and that's it. And we are open to new users submitting their targets, but also new telescopes providing data. So this is the schema. I'm going to quickly go through how it operates. So let's focus on the alerts, but it doesn't need to be alerts. It could be an asteroid, it could be an occultation event, it could be a quasar varying over a time scale of 2 years. So there is some source of information. There is a target of interest, right? It can come from Gaia, or ZTF, any other surveys from space, from the ground, and then it goes through brokers. It can go to AstroColibri, and then the users, the scientists or people interested in these particular targets, they can cherry pick their favorite targets, right? So, for example, someone has found 10 candidates for gravitational wave optical counterparts, right? Or there is one event called Gaia 20 FNR, and we need to observe it for 1 year. So these are the kind of observing requests which we then accept in form of targets. You create a target in BHTOM, and this is where BHTOM takes over. And we communicate with the network of telescope, and your telescope can be there. And we communicate. We tell you, okay, this is a new target which has been submitted, or this is the targets for this week, which require some observations, time domain observations. Whenever a telescope takes an image, then the data is transferred not to the users who requested this, but straight back to us for the processing. Of course, as I said, we also query the archival data, which supplements and gives a nice overview what's going on with that target. And in BHTOM, we process the data and we deliver the science-ready data to the users. So we separate these observing requests from the telescopes so that then the users, let's say scientists or people interested in some particular objects, they can get their data on their computers almost as soon as possible, as soon as it's processed, and they don't have to write any proposals, they don't have to apply for time, they don't have to communicate with many telescopes. We do it on their behalf so that they can focus on publications. As you could see, we write papers together with these users, and all of this can be scripted. These days, everything can be or should be automatized. So there could be a data flow from the alerts, through brokers, through filtering, observing requests, and then data processing. Everything can be automatized by robots. So here are some examples of the images, and the emphasis I wanted to make that we process the data. So everything is automated from the image request to science-ready data. We take the FITS files from the telescopes. One caveat is that we like to have the FITS files which are calibrated, meaning that they're bias corrected, dark corrected, and flat field corrected, because this expertise belongs typically to the actual telescope. People know their telescope best, so this is how they know how to calibrate them correctly. Of course, we can provide some support how to do that, but I guess most of you know how to do this. Once the image is calibrated, it is sent to us. It can be scripted, can be automatized, and then we do the PSF photometry, we do the astrometry. You don't have to do that on your side at all. We just take the raw image from you, and then we identify all the targets on that very image. We identify our target of interest on that very image. We standardize the measurements. We actually automatically determine which filter your data were taken with. We find the best matching standard filter to your data, so we calibrate that out. We use Gaia synthetic photometry as the main reference because it's whole sky, it's Johnson and Sloan. And then we produce a measurement from your image, right? So the target requested gets a measurement, and all you have to do is to submit your feeds file to our system. And then the data is downloadable for all registered users, and you can see your own data point on the light curve. Just to show you some examples of different science cases. So here we have an AGN. At the top, you see there is a lot of archival data for that AGN, including some radio data. And it spans 20 years, so there is some current data and some new observations as well. Then there is the famous supernova 2023 IXF. You see the light curve spanning more than a year. And this is all collected through our network of telescopes, supplemented with SWIFT observations from space and NEOWISE infrared data as well. Here you see Gaia 22 DKV. This is the event microlensing event where we found this tiny blip, which is due to a planet. And this has been published as this was probably the very first planet found by Gaia. By the way, Gaia was meant to find planets with astrometry, and there will be plenty, but this one was found from microlensing, and we contributed with our data points to it. More examples. As I said, we are not biased. We can observe any interesting time domain target wherever it is. So there is an eruptive variable, for example, which varies like crazy, and there is beautifully covered light curve there. There is another supernova here, and then another microlensing event, which we observed for many, many months with lots of data points. Some statistics. So far we have 450 users registered, and there's 400 targets which are currently requested for observations of different types, of different magnitudes, of course. And so far, in the last 2 years, we've processed more than 200,000 observations. Typically, we process something like 10,000 images per week. And we are now improving our hardware so that then we can process more, and we'll be ready to accept more requests for processing images. And we stored more than 20 million observations, including the archival data in our database. And of course, as I said, we invite new telescopes which can contribute whatever is the amount of time anyone can contribute. It counts. If you can observe, for a couple of hours every month, this is extremely useful because for some targets we need observations every month, right? Or you can see which target is now currently of interest, and you can contribute with your data point. Or if you can donate, more time, that's even better. So we're open for any cooperation. The more, the merrier. That's the approach here. As I said, everything is programmable, and I hope we'll have some time to talk about this more. I see I'm running, out of time for this introduction slowly. So AstroCalibri is already connected. It's the first example of that you can directly click, essentially through one click of a button, without going to BHTOM itself. Actually, you can submit your target you identified through AstroCalibri, and that uses our API and goes directly to our system. I can show you some examples there, and we provide the scripts for that. So essentially, you don't have to use our graphical user interface at all. Everything can be scripted, and there is documentation, growing documentation, and evolving functionalities. Essentially, everything. All functionalities are accessible via API. There is a newsletter we run. You can register, or you can it's an open group, a Google group. You can look through, and every week we send statistics of how many data were collected, what are the targets currently of interest. So this is an open group. I encourage you to sign in. Last comment here is that recently we've started a foundation which we call European Astronomical Society of Small Telescopes, and it's EAST with double S. So the foundation role of the foundation is actually to expand the functionalities of BHTOM and reach out to outreach communities, kind of outside of science as well, pure science, right? BHTOM was built for scientists only, but it has the potential to be used by citizen scientists. And this is what we do under the umbrella of the foundation. So that's why I advertise it here. So we start coordinating some outreach activities, local and global, and we connect astronomers, professionals, and amateurs. We expand the network, but not only for science, but also for outreach. And also we're looking into space industry, where there is the need for small telescopes, as I described at the beginning. We work on the enhancing telescope technology, so improving the data processing, but also looking into hardware upgrades. And we fight for the dark sky, which is something what we should all do, because otherwise it will make us unemployed. And we seek new partners. And I'm happy to talk more about the foundation itself. But as I said, the BHTOM is the core of the foundation. We use this as the main tool for running the network of telescopes. And we have workshops. We've been running workshops related to Gaia, but now it has expanded essentially to meetings of the entire network. And I wanted to use this opportunity to advertise the forthcoming workshop, which is sponsored by ACME, by the way, and it's going to happen in end of September, beginning of October in La Laguna, in Tenerife. So a very nice place, very nice time, warm ocean, but also very interesting meeting to attend. So I hope some of you will join us there. Okay, I'll stop this part. I guess I can take some questions if there are any.
One from Stephen.
Yeah, actually, I had a couple of questions, if that's all right. The first one was that weird microlensing curve, that really, really weird spiky one. What was going on there?
Yeah. So this is a signature of a binary lens. If you have two lenses, then microlensing, gravitational lensing is not additive in a common sense. It's not like you add two bell shapes. It's actually way more complex. So what is lensing is this kind of caustics, something you see. So the space-time is curved in a very crazy way when you have two lenses. Something what you see at the bottom of the pool when there is sun lightening the surface. So the same happens with the space-time. It's curved in this funny, crazy, funky way. And what you see, what happens with the light, is it has these sharp changes of magnification. So you can have changes over a timescale of hours, which you might easily miss if you don't have the network of telescopes covering the whole globe. And this happened here actually. We were observing there were actually two caustics here, and we were waiting for this one to happen, the final rise, and we predicted something, and then we were off by a couple of hours because the whole model was different, right? And someone reported to us, it's fading now. And we had a very intensive Twitter campaign at the time. It was really fun. Yeah.
Wow.
So some things like this happen, and you need telescopes for that.
So this is the binary black hole or binary neutron star?
Unfortunately, this was not a black hole as we had hoped.
Okay.
This was just a binary main sequence stars.
Okay.
But we couldn't see them, right? We couldn't see them at all. We don't need to see any light because we could only sense the gravity of these two systems.
Glorious. So yeah, the other question I had was you had people who've contributed data co-authoring papers, which is absolutely fantastic. On some other projects I've been involved with, but not data collection projects, that's not been the thing that's been most valued. It's been other stuff like being named on a ESA or NASA press release or something like that. So my question is, I mean, I love this, but is it always what the volunteers want, or is it, or do they sometimes want other things?
Well, it's a very valid point, actually. This is something what we can offer. It doesn't cost us anything, right? So there's no money involved.
Yeah.
And, if we have already dozen of authors, there's no difference if it's 1 dozen or 5 dozens,
Yeah.
right? Yeah. These days, you write papers like this. But also, in many cases, actually, this is something what people do want, because, for example, some of the observatories we worked with, they were when they were included they were co-authoring. The people from that institute were co-authoring papers. Then they could take the papers, take it to their own funding agency, and say, "Look, our small telescope has contributed to this, refereed journal. Give us money," right?
Yep.
And it actually worked. And it worked in many cases. I was sometimes writing, support letters saying, yes, this telescope is crucial member of our network. And people were getting money from their own funding agencies. So this is what works. This is the schema we found out it works. I haven't heard about any other ways of paying back. I'm very open, and we're flexible, of course.
That's very interesting. Thank you.
See that there's a question in chat. So Matthew asks, for citizen astronomers, what type of telescope configuration is relevant? And photometry with some precise filter and spectroscopy with a minimum resolution required.
Yeah, that's the most valid question you can ask here, actually. We are open, let's say. Let's put it this way. You need to have a digital camera. That's the main thing. And CMOS these days, it's very common. And actually, I was skeptical at first, but then I saw data we managed to process through our system coming from CMOS cameras, and it looks no different than the high-grade CCDs. So CMOS are fine. And the field of view, typically, the larger the field of view, the better, because we use all the stars you have in the field of view to calibrate, right? If you have a very small field of view and there's not many stars in the field, it's difficult to calibrate in an absolute sense. This is something what we do. That's an advantage. But still, we have telescopes with, small 10 of arc minutes of field of view, and it works, right? Then in terms of filters, the more standard, the better, of course. Sloan, Johnson Cousin, of course, but we managed to calibrate out the differences of filters from standard RGB, for example. If you have a standard RGB camera, then we can process it out and calibrate it out. So that's not a limiting factor, right? In terms of aperture, as I said, it can be anything. And the targets we observe are of very different magnitudes. I'll get to this image here, for example, right? So, you see 1 meter telescope here, but also you see 40 centimeter telescope here. And depends, how good your tracking is, for example, right? If you can expose for 1 hour and your tracking is good enough, then you can actually contribute to very faint ones. If this is to be tested, I guess, through operation, and you can figure out, is your telescope suitable for 12 magnitude targets only, or you can go to fainter ones like 15 or 17 mag. But I assure you, there is plenty of targets at each magnitude range, so you will not be bored, even with small equipment. And then we process your data, and we see if the data is looking good, then we invite you to contribute more, right?